All right, let's break down that problem that Lambeau posed to his class, saying it would take them a whole semester to solve, and that Will solved on his bathroom mirror in a night. So this is the problem as it was stated on the blackboard in the hallway. First part was to find the adjacency matrix of this purple graph that I've drawn here. The second part was then to find the matrix giving the number of 3-step walks in that graph. The third part was to find the generating function for the walks from point I to point J. And then the fourth part was to find the generating function for walks from point 1 to point 3. This probably sounds like gobbledygook to most of you, but it's really, most of it is a sophomore level math major problem. It combines a little bit of graph theory and a little bit of linear algebra. Linear algebra is a course that would generally come after calculus 2. So the first thing we want to do is take a look at this purple graph and write down its adjacency matrix, whatever that means. So here's the graph, and an adjacency matrix for a graph. A matrix is just a sort of table of rows and columns, and in this case we're going to put numbers in those rows and columns. And so the adjacency matrix for a graph with 4 nodes, there's 4 vertices, 4 circles. The adjacency matrix would have a row and a column for every node. So in this particular case, 4 rows and 4 columns. And I'm going to label our rows and columns to keep them straight. So this will be row number 1, row number 2, row number 3, and row number 4. And then column number 1, column number 2, column number 3, and column number 4. And the idea is that in whatever row and column, so let's say here, row 1, column 2, we want to write the number of connections going from 1 to 2. So in this case, there's 1 direct connection from 1 to 2, so I would put a 1 right here. There's no loop from 1 back to 1, so I would put a 0 here. How many direct connections from 1 to 3? So from this circle marked 1 to this circle marked 3, there's no direct line, so I would put a 0 here. How many direct connections from 1 to 4? There's 1. So our next goal would be to look at how many direct connections there are from 2 to every other vertex in the graph. Try this one on your own. Pause the video, see if you can fill in the numbers in this row. The number of direct connections from 2 to 1 is 1. There's no line from 2 back to itself, so I would put a 0 here. In this space, I'm going from 2 to 3. There are 2 separate connections from 2 to 3, so I would write a 2 here. And then how many direct connections from 2 to 4? Well, there's 1 line, so I'd put a 1 here. All right, if you got that one right, pause here and then try and figure out the rest of the matrix. For filling in from 3 to 1, there are no direct connections. 3 to 2, there are 2 direct connections. 3 to itself, nothing. And 3 to 4, there are no direct connections. From 4 to 1, there is a single line. 4 to 2, there is another single line. 4 to 3, there's nothing. And 4 to 4, there's nothing. That's it. That's the whole adjacency matrix asked for in the first part of the Good Will Hunting problem. So this impossible problem that this professor supposedly put on the board to stump his graduate students, we've explained in just a few moments. Looking at the numbered nodes or vertices in the graph, we count the number of edges or lines directly connecting each pair. The number of lines from 1 to 1, from 1 to 2, 1 to 3, and so on. So this is the adjacency matrix for our graph, and I'm going to call it A for adjacency.